Unit 2, Lesson 5, Point, Segments, and Zigzags. So our learning goal is let's figure out when segments are congruent. Okay, so it's not just about triangles mapping onto triangles, but also segments. All right, and segments are made of points as well. So if we look at the warm-up, that's actually where they start, is they start with this whole concept of you have a point A, okay, and then you have a point B, which is on the same plane, right? And that just means they're both on the screen right there that you're staring at. And then they say A is congruent to B, all right? Now, it says try to prove this claim by explaining why you can be certain the claim can be true, or try to disprove this claim by explaining why the claim cannot be true. So if you can find a counterexample in which if, right, a certain thing is true, then, right, this part is false, you have disproved a claim. All right, well, I think I can prove this one. I mean, think about it. We have transformations, right? So transformations. In fact, I should probably be a little bit more explicit, and I should probably say rigid transformations. Okay, so how can we get point A to map onto point B, right? Or vice versa. We could do a translation, right? So let me copy, paste. There we go. So we could do a translation, right? That can map a point, in this case, point A onto point B, right? And a point is just a point. So they should be congruent to one another, all right? So translation uh, along or from AB, so along AB, right, which is the directed line segment. Or we could have also have done what? We could have done a reflection, right? And if you want to do a reflection perfectly, you would need to, right, think about the compass tool. And we've done this back in the day. So if you were to do a reflection, and I guess I'll name this point up here C, this point right here D. So that is a reflection across CD. So a reflection would have worked. Right, so a reflection, that also preserves distance, right? So a reflection could have worked. So let's see, we had translation, a reflection. We could have also done a rotation, right? So let's take a look at rotations. Let's say, here, let me pick a better point here. So, right, I want to pretend that's the midpoint right there. I'll call that point P. And if I rotate a trying to get my, oh, that's not going to happen. Still gives me like a parabola. I'm trying to go for like a semicircle. I'll tell you what. There you go. I'll just pretend that's a perfect circle. But that's a rotation, right? So rotation, 180 degrees around point P. So a rotation would have worked too. Okay. So with points, right, rigid transformations work like a charm. You have a lot of options, all right, to basically prove whether or not that point A is congruent to point B. All right. In this case, we can map using translations, reflections, or rotations. Oh, what about segments? Okay, so now they're getting a little bit more interesting. Segment AB. Okay, so we got segment AB. So let me draw that. We got A to B. And they say it has, let's see. So we're proving if AB is a segment in the plane and CD is a segment in the plane, they have the same length as AB. Then AB is congruent to CD. Okay, let's take a look at that. So the same length, right? Then they have to be congruent. So let's see. Let's label it CD. Okay, I know for sure these are the same length because I did a good old-fashioned copy and paste. Okay, but that can't be my answer. If we did a translation, right? Along A to C, right? If we did that, hopefully you're watching, right? If we did a translation to get A to C, notice how both A maps onto C, B maps onto D. All right, so a translation will do that. Okay. Thus, A would map onto C, and B would map onto D. Okay. Therefore, AB is congruent to CD. So a translation would work. Rotation, right? What about a rotation? What about a reflection? Would those also work? Okay. So this idea right here should work just fine with the idea of a translation. Oh, whoa. All right, let's look at this one. Zig, then zag. All right, they give us some information right away. They tell us that QR is already congruent to XY. So let's go ahead and highlight that. So we got QR to XY. And that's what that one little tally means, right? So that little tally right there, that's what it already means. Okay, so they give it to you. So I know I'm highlighting it, but the tallies are still trying to say the same thing for you. Okay. So let's see. They also tell us some other stuff. Let's see. So we got that. They tell us RS, okay, is congruent to YZ. All right, and the tallies again, right, will also tell us the same thing. And then they tell us the angles. So let's see, the angles RY, which is right here, is to, so angle R is congruent to angle Y. Okay. I know we talked about it for one of our short days, but this is side angle side. right? Side, angle, side. All right, so that does come in later on. So I don't think they're capitalizing on that idea right now. I think that's next lesson, but just FYI, that might be a scaffold there. All right, here are some statements about two zigzags. Put them in order to write the proof about the figures, QRS, and XYZ. Okay, so let's see. So these aren't in order. All right, so let's see. Therefore, figures, so this is number one. Therefore, figure QRS is congruent to XYZ. Well, that's what they wanted us to prove, right, in the order. Therefore usually goes at the very end. So I think number one is the end result. So that's probably going to be the last step out of all of them. All right, so one is definitely going to be the last. Okay, because keyword kind of tips me off is therefore. All right, so let's see. 2 says S prime. Oh, wow, S prime. As you can see, there is no S prime right now, right? S prime would come in probably later after you do some kind of transformation. So let me explain. All right, that's a little off. So here's S prime, here's Q prime, here's R prime. And what I'm trying to say is you would have to do some kind of transformation, okay? Either a translation or a reflection or a rotation, right? Something would have to be moving around for Q or for S prime to exist, all right? But we don't have that yet. So that's somewhere in the middle of our proof. And I'm just going to keep that out there. Actually, I'll just delete that for now. Okay. So S prime is somewhere in the middle. I don't know yet. Let's find the number 3. So number 3, so that's somewhere in the middle. So number 2 is in the middle somewhere. Okay. Number 3, let's see, segments QR and XY are the same length, so they are congruent. Therefore, there is a rigid motion that takes QR to XY. Oh, QR to XY. So they're talking about moving this now. So QR to XY looks like it's somewhere around here, right? Okay, I see that. I see what they're talking about. I feel like that's the first thing you should probably do. Let's see. Number 4, since S prime and Z are the same distance long from the same ray Y, they have to be in the same place. Well, that's after the fact of what we just did for number 3, right? Like they're looking at this piece in number 4. Number 3 is like, no, we got to move QR to map onto XY. I think that's where you need to start. Okay, so let me look at the other ones just out of paranoia. If necessary, reflect the image of figure QRS across XY to be sure the image of S, which is called S prime. Okay. Now they're talking about S prime again. In order to make the assumption for number 2, number 5 needs to happen first. Okay, so let me put them in order from what we just... So number 3 has to happen first. Again, number 3 was moving QRS, right, over to XY. So number 3 has to happen first. And let's look, because I think after 3 it's 5. So let me clean this up. Okay, let's say here's QR, here's RS. Again, after you move them, they're going to be called primes. Okay, so we do some kind of transformation to get QR to XY. Okay, I think that's what number 3 says, right? So they are congruent, therefore there is a rigid transformation or rigid motion that takes, let's see, is it a sequence? No, they just say, therefore there's a rigid motion that takes QR to XY. Apply that rigid motion to figure QRS. Okay, we just did. So they're there. And then it says, if necessary, for number 5, reflect the image of figure QRS across XY to be sure that image of S, which we call S prime, is on the same side of XY as Z. Same side. Oh, okay, so I see what they did. Okay, so watch this. This is what they're talking about, right? Notice how when I moved originally for step 3, I not only did a translation, but then I also did a rotation. What they're saying here is if you ended up doing something like this, with just a pure translation, that's what the timeout was number 5. Some kind of reflection to get S onto, so that's number 5. Okay. Now, I wonder why they didn't use a rotation. So looks like number 5 happens after number 3. Okay, then number 2 happens, right? Because now they're saying this, right, for the side. And then number 4, right. Okay, and then number 1. Okay, so that's the order there. That makes the most sense. All right, so in summary, when you have 2 figures like this, even if it's just line segments, you can find a certain order in which you can prove these things to be congruent. All right, prove these points, segments, or even zigzags to be congruent. All right, the order does matter, okay, in which you put in to your proof. But again, you can always think about transformations and think about the order in which your transformations would be to get these 2 figures to map onto one another. All right, that's it. Have a beautiful day.